Hello, everyone. Today we are going to finish section 7.2. We have one little piece to finish and do section 7.3, trigonometric substitutions. So let's finish section 7.2. So in section 7.2, we learned how to integrate trigonometric functions and mixes of sine multiplied by cosine, right? Or tangent and secant products. Both functions usually have the same argument, which is going to be like x, right? In this last part, we are going to learn how to integrate something like this. For example, sine of 2x multiplied by cosine of, say, 7x dx. So you see the difference. It's not just like the powers of sine and cosine. Actual powers of sine and cosine are the same over here. But the argument is different of sine and the cosine, right? If it was the same argument, we would just make a substitution and kind of move to the same argument u and have it same. But we have different argument for sine and cosine. How shall we work with problems like this? Well, guys, you probably remember somewhere in trigonometry, we learned some formulas. Let me remind you what kind of formulas. You probably remember formula sine of x plus y equals sine of x by cosine of y plus cosine of x by sine of y, right? So you probably recall this formula. We learned in trigonometry. That's a sine of sum of two angles. And we use this formula to find actually sine of double angle, right? If we have 2x here instead of x plus y, we're going to have sine, cosine, and another sine, cosine. Wow. If you compare my expression under the integral, it looks like a part of this expression, right? Just it has like missing the second part. What should we do with that? Well, if you consider over here sine of x minus y, you're going to basically have a very similar expression, just a minus between here, right? Sine of x, sine of y, minus cosine of x, sine of y. Now, if we add these two expressions, what are we going to have? Well, cosines are going to disappear. This term is going to double, and this is going to be just a sum of two sines, sine x plus y plus sine of x minus y. It's going to be equal to sine of x cosine of x. Now, to find sine of x cosine of x, we just need to divide this expression by 2, right? I'm going to put 1 over 2 in front and just divide this part by 2. What is going to give to us? We have a product over here with different arguments, x and y, right? On the left side, we do have just plain sine, some kind of different argument, and just another plain sine of some kind of different argument, and 1/2 in front. Let's try to use this formula on my example integral. Well, I think I'm going to put equal sign here and move my solution below. And I'm going to do a little curvy line over here to show that this is formula from trigonometry, actually two formulas from trigonometry, which we use to combine into, to convert the product into a sum of two sides. So what are we going to have? 1 over 2, right? According to the formula, we are supposed to calculate sine of x plus y. My x is actually 2x and my y is 7x. So I'm going to have of 2x plus 7x. Okay. My next one is going to be sine of x minus y. My x, again, argument of sine is 2x minus 7x, and over here dx. Well, 1/2 is going to appear in front of the whole expression because I was dividing everything by 2, right? And now I'm just going to simplify a little bit this expression. putting 1 half in front. And under the integral, I have sine of 2 plus 7 is 9x, right? And plus, and 2 minus 7 is minus 5x, right? So I'm going to have sine of minus 5x dx. I remember that sine is an odd function. Odd function means that this actually equals minus sine 5x. Now, guys, I'm just going to integrate this expression. I'm hoping that you guys already understand how to do simple substitution, which is like linear substitution. If you want to use 9x instead of dx, you just put 9 here and divide by 9 for here. So I'm going to have 1 over 9, and integral of sine is going to be what? Cosine of 9x. Well, when I differentiate cosine, I'm going to get minus sign. So I'll need extra minus in front to compensate for that, right? Now I just differentiated. Cosine of 9x is going to give me sine of 9x with minus, which cancels this minus, and multiplied by 9 because it's composition. So cancels this 9. Now, for this sine of 5x, because it was already minus, we are going to just have plus, and 1 over 5 cosine of 5x. Well, again, we differentiate cosine, we get sine, right? And 5 is going to appear from the argument. And there's going to be minus because derivative of cosine is minus sine, which we already have in front of our function. That's going to be it. And we'll need to add a constant. You see? Very kind of simple expression. Now, guys, there are more formulas like this, like we have over here. I'm going to label it 1 with star. There are 2 more formulas. It's formula 2 with star and 3 with star. You can always find them online or in a trigonometry book in your cell phone, anywhere. What are the differences? Here we have sine multiplied by cosine. 2 other formulas are sine multiplied by sine with 2 different arguments. And cosine multiplied by cosine with 2 different arguments. And these 2 formulas, instead of sine here, sum of sines, they are going to have a sum of cosines and difference of cosines. But actual formulas are going to be very similar. So guys, I'm going to ask you to solve by yourself next 2 examples. So, example number 1. Sine of 8x by cosine of 5x dx. Find indefinite integral. Example number 2. Integral from 0 to 2 sine pi 2 pi x by cosine of 5 pi x dx. This one is definite integral, has limits, so your final answer is going to be just enough. Okay, so that's going to be all about section 2, which kind of was a long section, right? Okay, so section 7.3 is trigonometric substitution. What is trigonometric substitution? Well, you probably ask me, we just did trigonometric integrals. Do we have more trigonometry? Yes, guys, actually, these are 2 different things. Actually, trigonometric substitution is going to bring you mostly to the integrals from section 7.2 because they don't appear from nowhere. Actually, they appear from trigonometric substitution. Why do we call them differently? Trigonometric integrals and trigonometric substitution. This is just a name. We need to separate them somehow. So we name 7.3 trigonometric substitution and 7.2 trigonometric integrals, though kind of, you need to understand what they mean, not important how to be call them. So what kind of problems trigonometric substitution is going to solve? Trigonometric substitution is going to solve problems like this. So integral of square root of 1 minus x squared dx. This problem cannot be solved by just substitution. Why? Oh, if we substitute, for example, u equals 1 minus x squared, then we are going to get a square root of u, right? Here. And du is going to be Again, square root, because if we solve it for dx, you are going to write down 1 minus x squared equals u. Solve it for x, you are going to have u minus 1 square root, and you differentiate it, it's still going to give you square root. So our goal in this problem is to get rid of the square root. We don't know how to integrate square roots. So I'm going to use in this section 3 or 2 major formulas to create some substitutions. Let me kind of write the formula somewhere here. So my first formula is going to be Pythagorean identity. Sine square of x plus cosine square of x equals 1. My second formula is going to be 1 plus tangent, my tangent is too long. Sorry guys, something happened to my pen. Tangent square of x equals secant square of x. So these two expressions are both Pythagorean identities. What I'm going to do, guys, I'm going to solve first expression or cosine square of x. So I'm going to write cosine square of x equals 1 minus sine square of x. And now I'm going to look for similarity between 1 minus sine square of x and 1 minus x squared. And I found out that's pretty similar. And it rolls into cosine square, from which we can extract the square root and just get cosine. So why don't we use a substitution x equals sine of theta? Oh, I'm not using x like I have it in my expression. Well, if I use x again here, it's going to be very, very strangely looking expression. X equals sine of x. It's going to look like an equation. So I'm changing it to theta, just because I introduce a new variable. Actually, my new variable is theta, but you see how I introduce it? I don't introduce it like theta equals something. I introduce it as x equals sine of theta. Actual theta here is equal what? Arc sine of x. But I'm not going to do it because it's easier for me to write down x equals sine. So what is going to happen when x equals sine? Let's see how my integral is going to look. Well, there's going to be a square root 1 minus sine square of theta, right? At the beginning. Now, what is going to be dx? Well, dx, derivative of sine is cosine of x, oh, cosine of theta, sorry. Cosine of theta, d theta. And that's what I'm going to put over here. Cosine of theta, d theta. So now I do know that this is cosine square of x, right? So when I extract the square root, I'm just going to get cosine of x, right? The square root is going to kill the square. We are going to have cosine of theta, d theta, which is going to give me cosine square of theta, d theta. And I do know how to calculate the integral like this, right? Remember in the previous section, we actually learned that this one can be integrated using double formula. So I'm going to convert this integral to double angle and then just calculate it, okay? So I'm going to continue writing down over here because my expression is going to become longer, longer, and longer. Remember double angle formula, it's 1 plus cosine of double angle 2 theta divided over 2 and d theta over here. Now I can just calculate it. 1 over 2 d theta is going to give me 1 over 2 theta. And integral of cosine is going to be what? Going to give me sine of 2 theta. To compensate for this 2, I have to divide by it. I also have one more 2 in denominator here. And that's going to be it. I found my integral. You probably will write down plus a constant and finish the problem. But actually, theta was not my original variable. So I'll need to go back to my original variable. How should I do this? Well, for theta, everything is easy. I'll just need to solve it for theta. Let me change my color and kind of green. 3, and write down this expression separately. So if x equals sine of theta, then sine inverse of x equals theta, right? So actually my theta equals sine inverse of x. I'm going to write on 1 over 2 sine inverse of x. What should I do with this expression? This expression is more complicated. Here I'm going to use a formula for double angle. So I'm going to consider sine of 2 theta as 2 sine of theta cosine of theta and divide it over 4. You probably ask me how it's going to help. Let's go back to black. Okay. So I'm copying the first expression, 1 over 2 sine inverse of x. Now, for the second expression, first I'll cancel 2 and 4 and write down just 1 over 2. Second, sine of theta from this expression is just equal to x, right? What is going to be cosine of theta? Well, cosine of theta, according to the formula, it's a square root of 1 minus x squared, right? Well, it's supposed to be 1 minus sine, but sine is equal to x, so it's going to give me this expression. Well, usually, guys, if everything is about 1 here, it's easy just guess. Okay, if like sine of x, you just plug over here theta, and that's 1 over minus sine of theta, and sine equals to x, so it's 1 minus x, and the cosine is a square root, right? Usually, guys, we are going to find this expression using a triangle. This is the right triangle. I'm going to apply the fact that x equals sine of theta. I remember that sine actually it's a ratio of opposite side over hypotenuse. Well, fortunately, x is just x. It's not like ratio, but we can always write down that sine of theta, imagine that this is angle theta, is equal to x over 1, right? So if opposite side is x, then hypotenuse is 1. And what is going to be this side? Well, according to Pythagorean theorem, going to be square root minus x squared. Now, if you look at this triangle and just calculate cosine of this angle theta, it's going to be adjacent side over 1, which is going to give me this expression. When do we need to use triangle? When your angle is not just kind of theta, can be something different, or when you are dealing with some coefficients. So you're going to see in the next examples when do we really need triangle. Here for this example, triangle is unnecessary. Okay, so guys, we solved our first problem, and I'm going to assign a problem for self-work. So for self-work, I want you to calculate next integral, x cubed square root of 1 minus x squared dx. And we are moving to our next integral. Our next integral, number 2, is going to look similar way, but instead of minus, it's going to have plus, and it's going to slightly change my substitution. Remember, guys, the rule of substitution is to roll expression out of 2 terms into 1 term. So we need to look which trigonometrical expression is kind of represents sum of 2 terms into 1 term. Let's go back to our formulas. And this expression is looking like this. That's a sum of 2 terms and represents into 1 term, right? So if I compare this expression to my expression with the square root, I probably will use substitution tangent instead of sine here. I'm going to write down that. Let's imagine that x equals tangent of theta. Now let's do dx. Remember the derivative of tangent is secant square of theta, d theta, and we are ready to do conversion. Oh yeah, I forgot about one thing. The formula actually has here 1, right? And my expression actually has over here 4. I'll need to get rid of 4. How? Well, the simplest way is to divide by 4 the whole expression. Then this 4 is going to become 1, and that's what I'm going to do. So I'm going to have x squared over 4 plus 1. And I'm going to, well, I cannot just divide over 4, right? I'll need to kind of multiply by 4 too. And that's going to be just 2 outside of the square root. Okay, so how I'll need to adjust my solution? Well, actually, there are very small adjustment. So now this whole expression must be tangent square. Means that I cannot just set x as tangent because otherwise it's going to be like tangent square over 4. But how about if I place over here 2 tangent? Then if I square it, it's going to be 4 tangent square, and 4 is going to cancel and give me actually what I need for Pythagorean identity tangent square plus 1. So I'm going to start. By the way, because I add 2 over here, I'll need to add 2 over here too, just because my substitution is not just tangent, but 2 tangent. Let's see how it's going to look. So now I have tangent square of theta plus 1 and 2, and I'm going to copy dx. So 2 secant square of theta d theta. And well, let's just simplify it. I know that this is secant square. So I'm going to have secant square, square root is going to produce just secant. And there are 2 more secants here. Secant, instead of secant, write it down side. Secant square of theta, then d theta. And we have to multiply by 2 and by 2, which I'm going to put in front. Okay, so if I combine all the secants, I'm going to have a secant cube of theta d theta. You probably recall that that was my special integral in chapter 7.2. And for that integral, we already calculated it's going to be equal to a long and complicated formula. So why don't we just recall this formula? It's 1/2 secant of theta, tangent of theta. It's not that difficult to remember. 1/2 ln of secant of theta plus tangent of theta. Let's simplify it a little bit. So if we multiply 4 by these 2 1/2, we are just going to get 2 and 2, right? 2 secant of theta, tangent of theta plus 2 ln secant of theta plus tangent of theta. Now guys, we need to go back to x. So let's see what we know. I'm going to write down back to x. Well, first, need to express tangent. Second, we'll need to express secant. Let's start with tangent. We have x over 2 equals tangent of theta. Kind of easy. So this one is equal x over 2. This one is equal x over 2. Now, how do we calculate secant? Here, guys, we are going to actually use a triangle. You'll understand how it works. This is theta, right? Tangent is opposite side or adjacent. What is hypotenuse? Hypotenuse is the square root of x squared plus 4. Now, secant is 1 over cosine. What is actually cosine from here? Cosine theta from here is adjacent side over hypotenuse, right? Secant of theta, which is 1 over cosine of theta, is going to be the same fraction flipped over x squared plus 4 over 2. Well, let's bring them back over here. So x squared plus 4 over 2. And here it's square root of x squared plus 4 over 2. So now I'm just going to write down everything in simplified form. So I think these 2 and these 2 are going to cancel, and I'm going to have x square root x squared plus 4, and this over 2 is not going to cancel. Okay, for ln, we are going to have 2 ln, and we do have this over 2 and this over 2. Square root of x squared plus 4 over 2 in x over 2. Now we are going to have plus a constant. Okay, guys, I'm going to ask you to think about one important thing. If you solve problems like this and compare your answer with the book answer, you're going to see that in the book answer, they don't have this over 2, neither here or here. I'm going to ask you a question. Why? Think before the next class. Why actually the book is not going to have these two denominators? Why they're dropping it? Is it like allowed to drop the denominator, or what is the reason why we can do it? Okay, so here self problem is going to be next. Besides thinking about the question, integrate x squared square root of x squared plus 9 dx. So this is not g, this is 9. And we are going to move to our third equation. Let me change the color. Kind of word was black. So example number 3. I'm going to calculate integral 9x squared minus 1 dx. If we compare our integral to the formula 1 plus tangent square of theta equals secant square of theta, it doesn't look like formula because we do have a something like variable minus 1, and here we have a sum equals to a square. Well, what we can do, guys, over here, we can move this one to the right side, and we can write down the tangent square of theta equals secant square of theta minus 1. Now all my expressions are matching. What substitution I'll need to do here to convert it into tangent square? Well, I'll need to substitute instead of 9x squared, secant square of theta, right? Well, I'm making this comparison to make sure that you understand that actually 3x is going to be secant of theta. Why it's going to be 3x? Well, extract the square root from both sides. That's going to be, right? Now, maybe you wish, guys, to divide by this 3 just to get pure x. X equals 1 over 3 secant of theta. And we are ready to convert our integral to our new variable. So instead of a square root, I already converted this one to secant. This one is going to be secant square of theta minus 1. And then dx. Oh, I did not calculate dx. I have to do it. Dx equals 1 over 3. Remember the derivative of secant. By the way, I wrote sine over here. Secant. Derivative of secant is what? Secant multiplied by tangent. Secant is a very strange function. Secant of theta multiplied by tangent of theta. Vectorial secant of theta multiplied by tangent of theta. Don't forget about 1 over 3. Over 3 and then d theta. Well, we'll need to convert this one into tangent square and extract the square root. I'm going to just write it on tangent square. And then we extract the square root, which is going to give us tangent of theta. So my integral is going to look like tangent of theta multiplied by secant of theta multiplied by tangent of theta. And 1 over 3 is going to be written from d theta. If you combine two tangents together, we are going to get 1 over 3 tangent square of theta secant of theta d theta. That was a third special integral we had last section, right? And I was asking you guys to kind of figure it out, but I hope that you did it already and you already know what it's going to be. So it's 1 over 3 coefficient and then 1 over 2 secant of theta tangent of theta minus 1 over 2 ln of secant of theta plus tangent of theta. And my parentheses is not looking like absolute value. Okay, so that's just a table integral. I'll need to go back to x again, the hardest part of this problem. So I think I already know certain stuff, right? I do know what is going to be secant. Secant from this expression is equal to 3x. Maybe I should combine this 1 over 3, 1 over 2, and 1 over 2 into one expression and write down 1 over 6. And here 3x instead of secant. What tangent is going to give? Well, I'll need to do the triangle. Theta. And the secant equals 3x. Remember that secant is 1 over cosine. So actually cosine is 1 over 3x. Cosine of theta is equal to 1 over 3x. So means that this is 1 and this is 3x. Opposite side, adjacent side over hypotenuse. And this one is going to be what? 9x squared, the square of 3x minus 1. So now, what is going to be the tangent? We need tangent, right? Tangent of theta is going to be opposite side, 9x squared minus 1 over 1. Well, over 1 is just over nothing, right? 9x squared minus 1. Minus ln. I took this 1 over 2 in front already was together, like. And this instead of secant, 3x, and instead of tangent, square root of 9 squared minus 1. Okay, well, we kind of did it, right? Guys, I want to point that sometimes number 3 looks like number 1 because it has like quadratic term and 1 or a number. But if you look carefully at these two expressions, they are not same. They are different because here we have square minus 1. And in number 1, we go back to number 1, we have 1 minus square. If you switch expression under the square root, it's supposed to switch the sign. And you cannot extract a square root out of negative 1. So these two expressions are essentially different and they will require different substitution. Don't forget about this. Now some little tricks using actually this substitution, which you can see in the book or in the homework. And here I forgot to write down self-problem. For self-solving, I want you to do integral of x squared or x squared minus 1 dx. So my next integral is going to be a tricky one. It's not going to look like one of these 3 expressions I was teaching you, right? You see that under the square root, we don't have binomial, we have trinomial. What should we do with trinomial, guys? Well, we need to turn trinomial into binomial, and then we can use our substitution. Let's do it. It's not going to be a short problem. It's going to take another like 10 minutes of our work. So, how do I turn this into binomials? A square minus x squared. Oh, I'll need to complete the square for expression with x. 3 minus 2x minus x squared equals. Well, what is missing to complete the square with x expression? Well, x squared, I'm going to put minus here and put something like this. 2x plus x squared. X squared plus 2x plus what is going to make it turn into a perfect square? Plus 1, right? 1 was missing to complete the square here. Well, it looks like we just subtracted 1 here, right? Additional 1, which was not in the original expression. We have to add it to not change our expression. And then combining 3 and this artificial 1, we're going to have 4 minus. This one is going to turn into a perfect square x plus 1 squared. And our trinomial is becoming binomial. So let's write it down now in new shape. 4 minus x plus 1 squared dx. Now, guys, what we can do, there are two ways to solve this problem. Usually, we don't have any complicated expression instead of x here, right? We just set up, okay, there is something minus x squared is going to give us sine substitution. But actually, because it's more complicated, doesn't mean that it's not going to be sine. So watch what substitution I'm going to make over here. And you can do the same, just jumping a couple of steps. Well, first, we don't need 4, right? 4 is going to be here. So basically, x plus 1 squared over 4 must be equal to sine square of theta. Maybe that's not equal sign here because I'm planning to continue the integral. So I'm just trying to show what substitution is going to be. If you extract the square root, we are going to have x plus 1 over 2 equals sine of theta. So kind of similar substitution. Now we just need to calculate what is going to be x and what is going to be dx. How do we find x? To solve for x. To solve for x, I'm going to multiply both sides by 2 and then subtract 1, right? 2 here cancels, and I have x equals 2 sine theta minus 1. That's what I'm going to write down instead of x. The numerator, 2 sine of theta minus 1. Well, in denominator, when I was taking 4, kind of dividing by 4, I'll need to multiply by 4. So I'm going to have under the square root 4 sine 4, sorry, 1 minus sine square of theta. So, this 4 was kind of, I took it outside of parentheses. So I write down 1 minus x plus 1 squared over 4. That's from where we got this one. Okay. And dx plus step. Derivative is 2 cosine of theta d theta. I'm going to combine everything. Then take it to move over here. So combining everything is going to give me 2 sine of theta minus 1 by 2 cosine of theta. And in denominator, this one is going to turn into cosine square. And then square root of 4 cosine square is going to give me just 2 cosine of theta. Very convenient, actually. This one is going to cancel. And I just have 2 sine of theta minus 1 d theta, which is easy to integrate. And that's going to give me 2 cosine of theta, right? Minus theta. And probably minus here, because if I differentiate cosine, I'm supposed to get minus sine. So I'll need extra minus here. Now, guys, again, we have to go back to x. And that's the worst part of the problem. Let's do it one more time. But that's the last problem we are solving. So we're supposed to kind of be happy. Let's go back. Where did we start our substitution? Substitution was actually here, right? So our substitution was x, well, this expression, right? We need to know theta. Maybe we go back to this one and write down that x plus 1 over 2 equals sine of theta. Now, how do we find theta? To find theta, we need to cancel this sign. What cancels sign is sine inverse, right? So we'll take sine inverse of x plus 1 over 2 equals sine inverse sine of theta. Here they cancel and give me just theta, and here we do have the sine inverse. For cosine triangle. Sine is opposite side, x plus 1, opposite side over hypotenuse. The adjacent side is going to be what? 4 minus x plus 1 squared. Usually, guys, in the final expression, you are going to get that whatever you had combined everything, 4 minus some stuff, right? And of course, this can be converted into 3 minus 2x minus x squared if you wish. Because if you open this parenthesis, you are going to. Now, cosine is going to be adjacent side over hypotenuse, which is 3 minus 2x minus x squared over 2, and you just plug everything back into original integral. Minus 2, 3 minus 2x minus x squared over 2 minus, and my theta is sine inverse of this complicated expression, x plus 1 over 2. Well, I don't want to rewrite everything just because I want to cancel this, so I'm just going to add a constant. That's going to be my final answer. Yeah, guys. There are not like many different cases, but there are many different variations of how everything can look. I think that's all in this section 7.3, kind of short section with lots of variations. I'm going to place over here self-problem for practice, and I think we're going to finish at this point. So dx divided over square root of x squared plus 2x plus 5. Here you will need to complete the square 2, and substitution is not going to be sine. It's going to be a different one. Okay, I think that's all. And do your homework and prepare these self problems for our class.